Let's begin lecture. Okay. Um, here's our outline for today. Um, this SARC tutoring is available. Now, the Friday tutor, I believe Amaris, she texted me yesterday about not helping you guys out with your homework. That's her normal policy. So we're going to follow that. All right. And I guess a bunch of you or some of you went over there to get coaching on that, which normally that's all right. And if you come to office hours with me, that's kind of what we do. We kind of work on homework and stuff, various things. But that's her policy, so we're going to respect that. So just keep that in mind. Now, studying for other stuff and any problems that I say that you should use to study, not for a grade, then yeah, that's kosher. Okay. Now we're going to collect homework starting with last names N through Z. Bring them on up. Last name N O P Q R S. Just slap them right here. Okay. I see triangles. I see equations. I see diagram. I see a spaceship. Nice. Okay, thank you, Austin.
How you doing this morning?
Okay, Steve, man. Got it? Good. Anybody else? Esther? Okay, let's go. Move it. Okay. Okay, now the rest of yous. Bring it on up to the front. Uh-oh. Is there somebody with notebook paper here? No. Good. Just slap them up here. Okay, this is Fairgrave. So this is good. We only have one homework. Fairgrave, are you here yet? Mitchell? All right. I'll keep that in my pile. And do you have an envelope to put yours in?
Not a good idea. Yeah.
This is the old. This is the old one. Okay. Yeah.
I heard N through Z, not N through Z.
N through Z.
Yeah, I heard N through Z, so I think I put mine in there.
You put my.
I put my last name starts with M, so I put mine in there.
All right. I'll take care of it.
All right.
Don't worry. All right. So this is your pile over here. Okay. Anybody else? One more. Derek, you got yours in? Okay. 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 Let's get back to work. Shh, 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 shh. Sealy? Sealing. Is that, do you have to turn that in? All right. Okay, now, this was a battleship problem versus aliens, kind of like in this movie. This is a real battleship shell. This is a 16-inch shell. on one of the big battleships. I think this is about the biggest they got. That the blue. Shh, 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 shh. You ready? Maybe take your earbuds out so you can hear what I say. All right. This is a real shell. This is from a big battle wagon, a battleship, like the USS Missouri and so forth. The blue part is the actual shell, and those white cylinders behind it, those are bags of gunpowder. And that's how they do it. They pack in the gun, they load the shell in, and then they put in the bags of gunpowder, and that shows you that you can have variable velocity, depending on the number of bags of gunpowder that you put in there, right? So maximum is 6, and those things can fire for miles, just like the one that we were working with. So this is a normal. Well, I don't know if you should call it normal, but it's an existent system, and the dimensions that we were looking at were normal for Navy gunfire. So even though there's no such thing as aliens, so far as we know, although sometimes I do check through the class to see if there's any aliens, but right now I think everybody in here is some kind of a human. So let's do a clicker, quick and bodacious clicker question. So turn on your clicker, and let's do a quick multiple choice question. Here it is. What was your perfect velocity? Okay, and hopefully everybody got this one right. Okay, so 20 seconds. 10 seconds. 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay. All right, now let's take a look at some of the answers here. And there's a big pile over here at 507, and that is the correct answer. These two up here, A and B, those are like components. That's the X component of. I think the first one is the X component of the. Actually, I have my notes here. Yeah, 353.33 is the X component of the first shot, and then the perfect shot, the X component is 358.54 is what I had. Right. So if you had one of those, which a bunch of you did, you were not. If that was your final answer, what you want to do. Well, we're going to go over what you want to do on that. The full magnitude is what you want. That's the muzzle velocity, what they call the muzzle velocity, 507 meters per second. A few of you wrote none of the above, but we'll grade those in, and hopefully you guys letter N for November through the end of the alphabet. You guys will be. I'll have it back for you on Thursday instead of. I had company from out of town last week, so I was just extremely busy with a lot of stuff, so that's why I didn't get the grading done as fast as I wanted to. And I really love grading homework, not. All right, so let's go over the basic strategy here. First thing you got to do is figure out the coordinates of the aliens. And up there on the mountaintop. Now you already have the elevation. But if you do a little bit of trig, you can figure out that the x coordinate is 2,300 or 23,750 meters, 23.75 kilometers. By the way, hopefully everybody converted everything into meters from the, from the given information. And there's bunches of ways to do that. You can use similar triangles, do a little trig. You can even do y equals mx plus b for the equation of the line representing the back slope of the volcano where A is. So you can figure that out. Then the other thing you got to do, you got to do that. Number one, you got to find your target, okay, in 2 dimensions. So you got that. Eventually, doing some trig. Then you got to write equations of motion, and then you execute or you use the equations of motion for the first shot. Now the first shot lets you figure out everything in the equations of motion, except for the time. It's a time evolution equation. So t is going to be a variable, and you figure out where your t is and stuff. And the first shots, if you use that equation of motion to check the y coordinate of the first or the x coordinate, either one, for the first shot, you find out that the first shot's y coordinate is too small. In other words, it doesn't quite make it to A. It's going to land either uphill from A or possibly on the other side, the near side of the volcano. So those are your first. And so the answer to the first basically true-false question, it was a multiple choice, I guess, was it's short. And so the answer is to put in more velocity. And that's what you need to figure out for the last part of the problem. What's the perfect muzzle velocity to actually hit point A with your explosive shell? And so, and believe me, if you have that big 16, let's say that thing's several feet long, right? So you drop a bomb of that size on an alien spaceship, unless it's like in Independence Day, that thing was ginormous. And also the Death Star, that was pretty big. You have to have direct hit in the nuclear core, like what Luke Skywalker was able to do. But other than that, most alien spaceships, you can, pretty much take them out of the equation with one shot. So let's look at the strategy and solution. We're going to go to the document cam now for a few minutes. And can you switch me over, please? All right, so you can see what my solution looks like, and I'll be putting this up in web courses a little bit later today, maybe tonight. But what I want to do is talk to you about how to handle this problem. Now, here's something I worked out last time. This is the y equals mx plus b method for. Can you give me my pencil case? Let me get out my. Okay, so this is the y equals mx plus b method for this line here from point P to point S2. So the slope is -1/5 because this is 3 here. This middle segment here from the midpoint at the base up to the peak is 3 kilometers, and this is 15 from S1 over to M. So it's a slope. This one's a positive 1/5. And this one over here on the right, from the peak back down to the other side, S2, that's a slope of -1/5. So your slope is -1/5, and then you have a couple different points on the line that you can use. The easiest one to use, and I'm assuming that this is the origin of coordinates over here. By the way, that was one of the streamlining assumptions that you can usually make in a problem of this kind, especially when you get to the equations of motion. Anyway, so 35 comma 0, that's S2, right? So we know that the point goes through that, the line goes through that point, and so you just put in the coordinates, y minus the y coordinate of S2, which is 0, and then x minus the x coordinate of S2, which is 35, in parentheses, and then a slope of negative 1/5 outside there. So that gives you the slope intercept form, and this is in kilometers, which is all right. You can figure this out in kilometers and then convert to meters. And so so we know that that the y coordinate here is 2250. So you plug that in over here on the left, and then you figure out what A is, and it works out that A has to be what, 3,500? What was it? This was 11,000. So then you do some subtractions and stuff. You can figure out this distance, which is 23,750. Okay, so you could do that, or you could do this similar triangle here, and then and you may think, well, how's the y equals mx plus b and similar triangle strategy similar? How are they the same? They're actually the same because the tangent of this slope here is negative 1/5. So that's the slope is the tangent of the tilt angle of the line that you're looking at. So just remember that when you're trying to figure out these these kind of problems. As I've said before, triangles are all over the place in this problem. Now, so you have the coordinates 23,750 comma 2250 for your mountaintop point, or for your mountain stronghold. Okay, so here's your aliens over here, and this is 23,750 meters comma 2250 meters, and your battleship is over here, so this is point B, and let's call that 0 comma 0. And what we want to do is get a perfect parabola with a launch angle of 45 that passes right through this point. But what I asked you first to do was check the parabola of the first shot. And so the first shot is, here's your 45, your square. Okay, and here's your first, here's V0 for the first shot, and this is 500 meters per second. And so you can figure out that the two sides are 353.33 meters per second. And same thing down here, so I'll just put dittos down there, okay, because it's 45-degree angle here. Oh, I was going to make a mention about something I saw on the homeworks last time. I'll do that on Thursday. Anyway, so here's your first shot. There's the initial conditions on the velocity, and so for the equations of motion, in general, the equation of motion is x of 0 plus v x of 0 times t plus nothing else, because it's not accelerating. And y of t is equal to y of 0 plus vy of 0. So that's this part. This is vy of 0 over here, times t plus 1/2 gt squared. And in this equation, you use g equal to negative 9.8. All right. Now that's in general. For us, if we just declare this point B here to be 0, 0, then that simplifies. Where's my pencil case? Oh, here it is. Okay, I'll cross this out with red. Okay, so these two guys can go. You can cancel those out, and that makes things a little bit easier. All right, so your basic for this shot, the first shot and the perfect shot, you're going to be working with basically a formula that looks like this: some velocity times t, and just as a note, v is equal to vx of 0. And because it's 45 degrees, you use the same in the y of t equation, but it's just 1/2 gt squared. All right, so those are the two. That's the general equation if you have a 45-degree initial velocity. If you have something else, then you got to do trig, and it's much more complicated, but you can still grind it out. Ooh, that inspires me for quiz 1. A non-45-degree angle that's not tortuous. So what would be a non-45-degree angle that's not completely bodacious? 30-60, maybe a 3-4-5. Okay, so if I did something like this on quiz 1, it wouldn't be a 30-degree or a 3-4-5 because that would make it too easy. So just kidding. It'll be whatever, it. But hey, you guys, quiz 1 is coming up next Tuesday. It's going to be a lot like a homework problem. The test, on my tests, this is the same format. And with the exception that I might have the diagram on another page to save space. And also we might have a couple 3 multiple choice questions like on the back. All right. And you'll be doing those with eye clickers if we do that. I'll tell you what we'll do on Thursday for the exam. But it's going to be like this. You're going to turn in 1 page. And there might be a cover page, with a diagram on it and your name and PID and all that stuff. But it's going to be, so that's why I'm drilling you hard on these. And a lot of you guys, the homework 2 that I just handed back, a lot of you guys got rocked. All right. But you can redeem yourself on quiz 1. And then, of course, we're going to have some extra homework along the way and maybe some bonus point homework at the end of the semester. So you'll be able to redeem yourself if you got blazed on homework 1, 2, or this one, which you'll get back on Thursday. Anyway, so these are the equations of motion. And, you can, I saw some students flailing with, oh my goodness, on homework 2, I saw students flailing with all these cosine of theta and sine of theta, and they were lugging around all these big expressions. And really all you need to do is, try to simplify your notation, with the symbol V, meaning Vx of 0, simply so that you don't have to keep writing V subscript X of 0 and stuff. And that, makes the notation a little bit easier. All right, so the first shot, what you want to do is use the information that you know. Now you can write down for X, 23,750 meters is equal to, now for this one, we actually have the Vx of 0. So it's 353.33 meters per second times t. And you can write down 2250 meters equal to the same 353.33 meters per second times t plus 1/2 gt squared. Okay. Now 1/2 gt squared is actually, I'll write this one out. in numbers as well. Ooh, this is my bad pencil. I shouldn't be using this. Some of these pencils don't show up on the photocopier for beans. Okay, so I have to be careful about which I use. Okay. So this is negative 4.9 meters per second squared times t squared. Now, either of these two equations, so so here's your general, okay, up here in the box. Here's one particular case, and this one, you don't know how far it takes to get out either distance. And in fact, if you solve for t here at 2250, you got to use a quadratic formula to figure out t. And that's a pain in the you-know-what. All right, but this one's a little bit easier, and that's what I did. Okay, so this means that the time to get out to 23,750 is about 67.18 seconds to get to x subscript a. All right, now does that amount of time, what's the elevation at that time? That's the next question. All right, and that'll tell you where you are on the volcano. You're not going to, obviously I designed it so you're not going to have that be the perfect shot, 500 meters per second. All right, so you got, that's part 2 of the problem. So this one's not going to be elevation. When we plug in 67.18 down here, it's not going to work. All right. So what you do is you figure out y of 67.18 seconds, and you put it in here, 353.33 meters per second times t. And actually, you already know what that is. That's 23,750. Plus, then you do this one, negative 4.9 meters per second squared times the square of 67.18 quantity squared. And what you get for this one, according to my notes, is 1638.8. And that's definitely somewhere down here. So I'll put a little X here in the diagram. So that's on the equation that's on the parabola for the first shot. So the first shot is going to look something like this. Let me do it in red. Okay, so it's going to be up here. So it's going to arc out like this. And it's not going to quite get, it might go a little bit higher than the mountaintop. This is kind of a freehand sketch, but it's not going to get to 22,750. So this is short. And so the question, does the round hit at the alien's point A? Does it land uphill or downhill? The answer is it lands uphill from them, because it's somewhere up here on this side of the mountain, or possibly up here. If you work it out on a computer, you can, get it all. You can figure out exactly where it hits this point up here. Matter of fact, the way to do it is to use this half of the equation and then set that equal to the way that you would find, the exact impact point is by setting this half of the equation equal to, now what was that? That other one? Equal to this equation over here. So that's negative 1/5 x plus 7. And then you can figure, and so you would put negative 1/5 times 23,750 meters plus 7,000 meters, and then you'd be able to find the actual position where it where it cuts through, whether it's up here. Well, that's if it does intersect. If it intersects this line, you'll be able to figure it out that way. If it intersects this line over here, the front slope of it, you would have to use the equation for that particular line. But anyways, you could do that if you wanted to. All right, now let's keep going. So the question now is, decide if this round hits uphill. It hits uphill. Does it need? Is it for the perfect hit? Do you need more speed or less speed? The answer is you need a little bit more. You want to give it a little bit more oomph for the shot. So now the perfect shot. This is a little bit different, but you still use these equations of motion up here. All right. And in this equation of motion, you don't specify V. That's going to be an unknown. That's what you don't know. So you write down 23,750. Oops, wrong pencil. No, this is the wrong pencil too. What am I doing here? Come on, Dr. B. These things are not dark enough. So 23,750 equals VT. Now we don't know what V is because we're trying to figure that out. And we don't know the time to get out there, but we insist that these two equations and this one you can write down as negative 4.9 meters per second squared times t squared. So these are two equations, two unknowns, so you can solve for those. And there's various ways to do it. You know, the one that my students figured, I mean, you can use this one down here and solve for use the quadratic formula down here, but that would be a pain in the burp. So what my students said yesterday in office hours, they said, well, Dr. B, why don't we just put in 23,750 down here for VT, because that's what VT is equal to. Okay, so you put in 2250 meters equals 23,750 meters plus minus 4.9 meters per second squared times t squared, and now you're basically done. You've got the answer for that. Okay, so t works out to be go to the next page here. Okay, so t here works out to be 66.24 seconds. So it's a little bit shorter, about a second less time. And the reason for that is it's faster. All right. Now, how do you get the rectangle, the square for this one? You want to get, so here's page 2, and let me make this one a little bit bigger. So this is 6 by 6. Okay, so here's your perfect shot. And we don't know what the perfect shot is, but we know that V and V are here, and this is still 45 degrees. And so all you got to do is figure out that V is equal to 23,750 meters divided by 66.24 seconds. And that gives you just a little bit more speed, 358.54 meters per second. So up here you got 358.54 meters per second, and you got dittos down here. And so the trig means that up here, v of 0, the muzzle velocity is just that stuff divided by the cosine of and so my final answer will just round it off to 3 places. Okay, so you do a little trig and you get that. All right, so that's how that works. And you know, and this is what mine looks like. I've got, if you look at my solution, we were kind of running out of space on this, and some of the students mentioned it. So I used my first diagram, I used this diagram, and I made a little subtriangle up here for similar triangles. And that's what I used. I used similar triangles instead of y equals mx plus b. And then here's my first square for 500 meters per second. And then here's the one that here's my new velocity square. So, you know, and here's all the work and stuff. Now, here's the two equations of motion that I was just talking about, 23,750 and so forth. So you can figure out T 66.24. Now here's how I'm grading it. The two equations of motion, 3 points, your two decisions. Those are like Scantron questions, 1 point each. And then 7 for everything else. So there's going to be hopefully a lot of partial credit on that. Question, Seeley. No, I didn't specify how to round off, but on the exam I'll do that. Okay, and like when we do clicker questions, I usually tell you how to round off if it's a numeric problem, and I'll do the same on the test, so there's no ambiguity. All right. Now, just to remind you, the quiz next Tuesday, you're going to have a problem like this. Okay. Well, I take that back. It's going to be one page and maybe a little more compact up at the top, maybe not quite as much preamble as this one. Maybe a diagram on a cover page, but you're going to have to, you know, and I'm going to have a little grading box down here. So just keep that in mind as you prepare mentally for the exam. Now we're going to do a little bit more document cam work here, but right now I want to go. Can you swap me back to the laptop, please? All right, so here's our and just a blurb about the quiz next Tuesday. We've talked about it already. All right, now, next thing I want to do with you is I want to check the pendulum frequency situation. I did some analysis of your data, the big data set. Did I post that in web courses? The data set? Yeah. Okay, and the data set had all the different groups and stuff like that. And let's do some document camera work here. And can you switch me over to the document cam? All right. Now, I'll just continue on this page. And I'll draw, let me use my specs. I want to make a careful drawing here. I'm going to draw a pendulum hanging from a ceiling right here. So here's my ceiling. Here's some cross hatching. Okay, so this is the pendulum. And now here's my vertical. My attachment point is right here. So I'm going to draw a vertical line downward. And then I'm going to draw I'll put my pendulum over here, and then its length is L. And this is the angle theta. So this is like the angle that you pull it out to when you start it. And then here's the similar one. I'll do it in red. Okay. Okay, so it swings out as far as that. All right, now let me check some of my notes here. Hold on a second. I want to make sure I get this set up correctly. See, look at my notes here. And I got all kinds of notes. See that big cross out? See that quadratic formula in there? And when I got to that point, I thought, nah, I'm not going to do that. It's too messed up. Okay. All right. So let's tear this out. Okay, so what we're going to do, let's say that the pendulum swings down this far, and I'll draw the pendulum up here. So it has an arc like this. All right, that looks about right. All right, and it's going back and forth, the way pendulums do. And what I'm going to do is I'm going to study the pendulum in this position right now. And let's just call this position x comma y. All right. And let's set up the coordinate system. Let's put the very bottom of the pendulum swing to just be tangent to the x-axis. All right. And let's make this vertical. Let's make this the y-axis. So it's going straight through along my dotted line there. Okay, so that's the y-axis up there. Okay. All right. Now the coordinates here, in terms of L and theta, are what we want. We want to try to get that, and what we're going to really try to do is get the potential energy, which is mgy. All right, and that's what we've already talked about that a couple weeks ago. Potential energy mgy, and what I want to do is convert that into u of theta. All right, and that's going to be important for us in this derivation. All right, so let's think about these triangles and squares and rectangles down here, and so the y coordinate is a little tricky. Let's see. X. Here's the x coordinate right here. That part of the right triangle. So that's L times sine theta. So x is easy. That's equal to L times the sine of theta. Okay. But y is a little bit trickier because when theta is equal to 0, it's equal to 0. And really, y is this little chunk right here, all right, in this coordinate system. So it's it's equal to length L minus whatever this vertical part of the right triangle is. So that's L times cosine theta. All right, and that simplifies to L times the quantity 1 minus cosine theta. All right, and now that allows us to trade in the Y and get a theta dependence. All right, so that's nice. Now, a couple things that we're going to need in this is the small angle approximations. So we're going to do small angle oscillation. So that means you just pull it out, you know, a couple degrees, and it'll still, and you guys might not have noticed this, but it still has the same period, whether you pull it out a lot or a little bit. All right. And that's why pendulums are so nice. So the small angle approximation for theta, for sine theta, are needed here. Okay, so for sine of theta, you know, the power, do you guys know about power series? The Maclaurin series and the Taylor. Okay, so for sine theta, it starts out with you know, or sine of x. The power series is x, and then I think it's minus 1 over a third, or 1 over 3 factorial times 3 to the theta to the third power and stuff. So for small angle approximations, it's just theta. The first term in the series. All right. Now, if you have bigger angles, you can't use that. All right. Same thing over here. Cosine theta, I'll write it down over here. Cosine theta is approximately 1 minus 1/2 theta squared. All right. That's from the power series. And I'll just put down, I'll put an equal sign here. I'll put an equal sign here, and then I'll put plus dot dot dot. And you can look up the power series for cosine of theta. All right. Now, what we're going to use for the small angle approximation is cosine of theta approximately equal to 1 minus 1/2 theta squared. All right. So that's nice. All right. Now we're going to use that over here, and we're going to use it over here. All right. So x transforms to L times theta, all right, for small angle oscillations. So that's in this approximation. And hey, you guys, you engineers, you're going to be doing this out the wazoo. You're going to have a class called, I don't know what they call it here at UCF, small oscillations. Anybody taken that yet? Small oscillations or mechanical vibration? What do they have over there? Do you know? Okay, it's a class. You know, machines. You know, like your car. You're going down, and one of your tires is out of alignment or something. Your car starts to shake a little bit. That's a small vibration, and you want to keep it small. Otherwise, your car will shake apart, and you'll be in a crash and stuff. So you keep the speed down. But those are small vibrations. Anytime you see a machine, oh, you know what's cool? You put something, you know, I did this a couple of years ago out in Texas at a laundromat. You know, we were picking up my son at college for Christmas, and we had to do a load of his. He's about your guys' ages. At the time, he's about your guys' age. So we had to do this huge load of laundry that he left from the whole semester that, you know, this anyways, we had to do, and so we did like 2 or 3 washing machines loads, and then we had this one big dryer, industrial sized dryer. Actually, we had 2 dryers going, And one of them got out of balance. And oh my goodness, I thought that thing was going to explode. And there's nothing you can do. You just got to let it go. And hopefully it'll shut down, but it never shut down. But it finished. It survived. It was that dryer was just jumping all over the place. That's not small oscillations. But in this approximation, yeah, this is good. Now over here, we're going to put it in over here. So 1 minus cosine theta is approximately positive 1/2 theta squared. All right. So y transforms to approximately 1/2 L theta squared. All right. Make sure my notes are correct here. Okay. So 1/2 L theta squared. Now we'll put it in and we'll transform u of y, which is mgy, into u of theta, because we can now do it. Okay. It's mg times L over 2 times theta squared. All right. Now, as you know, you may not recall this from high school, but this is basically an oscillator potential. Okay. And you guys in physics, everybody in here is going to have to deal with quadratic potentials, quadratic potential energies all the time. Now, MGY itself, this is not an oscillator potential because that's for free fall. That's for, the y coordinate. But now if we're constrained to this circle, we can make this approximation, and now we have an oscillator potential. Now you may remember that for spring systems, the potential energy, anybody remember seeing this in high school? 1/2 kx squared? Raise your hand if you did. Just curious. Okay, that's a fair number of you. That's the oscillator potential, for like a mass on a spring like this. Okay, and the potential energy, the kinetic energy, is equal to 1/2 mv squared. Okay, and the same thing here. The kinetic energy of the pendulum is still 1/2 mv squared. So basically, whenever you see a theta here, you're going to have an oscillator situation. So what that means is that let's see. You can do it this way, or you can actually do it in terms of x. So let's change this. So there's my oscillator potential, and let's change one more time, and then I'll go to the next page. Let's change u of y from u of theta, and now let's go all the way back to u of x. Now we don't normally think of that, but this is a constrained system. It's usually for a gravitational system, there's no such thing as horizontal gravity, right? Except now we have a string constraining it to something other than a parabola or a straight down free fall. So we can write this. All right. Now, x is equal to, so we could say that x is equal to L theta. So this thing now can be changed to mg over L over 2L times x squared. All right. And now we have a potential energy function for a horizontal oscillation. So we can look at it either way as a horizontal oscillation or a vertical oscillation or a theta oscillation, either one. They're all oscillator potentials. And this one, we're going to look at this one because this one is going to be the clearest view of how we get to the formula for the frequency of this baby. All right, now I'm going to go to the next page. All right, and I'm going to rewrite u of x equal to 1/2 times the quantity mg over L times x squared. All right, and if we had a spring system, it would be 1/2 kx squared. And so the total energy of a spring system would be 1/2 mv squared plus 1/2 kx squared. And x squared, v squared is d by dt of x. So this would be 1/2 times m times dx by dt quantity squared plus 1/2 kx squared. Okay, so this leads to an equation of motion that's a differential equation. All right, and it's basically this, that the mass, if you do like a derivative of this, one more derivative with respect to time, you get this mx double dot. Oops, let me use grade school calculus notation. D squared x, so this is a second derivative with time, equals minus mg over L times x of t, right? And you can kind of see that up here. If you differentiate this thing here with respect to time, you get 2 times v squared, 2 times v times v dv by dt, and that's where the dv by dt comes in. Over here, if you differentiate x squared with respect to time, you get a 2x and then a dx by dt, and that's where this comes in. So this is equal. So this is a differential equation. You'll see these out the wazoo, all of you, in the next 2 or 3 years. Okay, this is a simple one for an oscillator system, and it means that d squared x by dt squared is basically equal to minus g over L times x of t. Okay, I've canceled out the x's. All right. Now that is similar to this is for our u of x, the pendulum. So the pendulum's u of x leads you to this equation and in this form. Now let me ask you a question. Let's look at this. Let's look at this equation here. This is a differential equation right here. The second derivative of x of t is proportional to, now g over L, those are constants. Okay, you know, some meters in the denominator and then positive 9.8 meters per second in the numerator. So this is a constant here, and this is x of t. So what kind of a function is it that if you differentiate it twice, you get the same function back times a constant? Periodic, that's exactly right. It's going to be a sine or a cosine. All right. So let's look at that. So let's say that x of t is equal to some amplitude a times the sine of some constant, we'll call it omega. Yes. And so x dx by dt is equal to, okay, so d by dt of sine is positive cosine, right? All right, so this is positive a, and then I have to bring the omega out, and then cosine of omega t. Okay, now the second derivative of that, of x of t, is equal to, okay, cosine, d by dt of a cosine is negative cosine, or negative sine? Is that correct? Okay, so this is a negative. Now I still have a, and I have another factor of omega, so that's negative a omega squared times sine of omega t. Yeah, so that's good. So my second derivative, oops, this should be d squared by dt squared. Right. Okay, so my second derivative of a sine is a sine of the same frequency, and I've got a constant out here. All right. Now, so up here, you know, that constant. All right. So this, let me modify this one more time. Minus omega squared times a sine of omega t. Okay, so that's minus omega squared times x of t. Okay, so we've drawn out that angular frequency omega, and hey, you guys, guess what? This stuff here, let me write it in red. This stuff here is equal to this stuff here. So for a hanging pendulum that we've got, the angular frequency squared is equal to this stuff. And actually, there's a minus sign in here too. So, so let's get to it. So what this means is, let's see. So if you go, and let me go over here to the right, omega squared is equal to minus g over L. Okay, now this is a positive number here, minus g. And you know the omega is equal to 2 pi times the regular frequency. Okay. And so so let's see. So omega is equal to the square root of minus g over L. And remembering, so we're not doing negative, we're not doing imaginary numbers here. That's just a positive 9.8 in the numerator. Okay, now that's equal to 2 pi times f. All right. And the reason that we call it a frequency is because this times the period is equal to 2 pi. So f is equal to 1 over the period. All right. And so so now let's look at our data. All right. So let's write it one more step here. Square root minus g over L is equal to 2 pi times 1 over the period. And so what that means is that in a pendulum, the period, now we're going to flip-flop this, the period is equal to 2 pi times the reciprocal. So this is minus L over G. Okay. And let's write this with a positive number inside. So this is 2 pi times the square root of L divided by the square root of 9.8 meters per second squared. And notice that the units here, the square root of per second squared is per second. So that'll go into the numerator. And then square root of a distance on top, square root of a meter down here, they cancel out. So basically, the units here are seconds. And that's good. So here's our formula for the period. 2 pi times the square root of L divided by the square root of 9.8 meters per second squared. So it's kind of an awkward way to write it, but that's what we're going to write it with. Okay. Now, can somebody calculate this? 2 pi over the square root of 9.8. Do you have a? Let's just double check that. Okay, so 2 times pi divided by 9.8 square rooted. So what do you get? 2.007? Anybody verify me? 2.00. Okay, 7. I use the pi button instead of 3.14. Okay, so this is about. So this is basically about 2.007 seconds. Now, well, times square root of L. All right, in seconds. All right. So now, so the data that we gathered. Let's go to the laptop. That's a long derivation for the frequency. Now, here's our theoretical frequency. All right. So this is, and you can see it up here in the upper left. There's my. So this is y and x instead of t and L, square root of L and stuff. But so think of y as being capital T, and think of x as being L. And look, we got a 2.071 out in front. All right, that's the 2 pi over square root of 9.8. Good. And here's L to the 0.5 power. What? What's a 0.5 power the same as? Square root, my friend. All right. So this is the black curve is the square root function. Okay. And the squares are all of our L's square rooted and then multiplied by 2.071. And it correlates exactly, R squared is equal to 1 relative to this power law trend line. All right. So my theoretical values of period should all be, these are the theoretical values for all the different L's. Remember, L's are on the horizontal axis. These are the theoretical values for all the L's that we collected, right? And so there's some gaps. There's some big ones up here. There's a gap down here and some small ones down here. Most everybody did, there's a whole lot of coverage down here, all right? So if our data followed the theory perfectly, if you guys didn't mess up like humans do, all your data would be right on this line. Okay, it's a square root line times 2.0071. All right, but that's not what we got. This is what we got. All right, wait a minute, that's my equation up there. Okay, This is what we got. All right, now look. Okay, so the red stuff is your measurements. Ooh, I misspelled measurement. The red stuff, and you can see there's a lot of slop in the data. The trend line for the red stuff is this thick red line. Now, R squared is 0.6474, which is not too bad, but it ain't 1. Right? The black trend line is exact because that's how we graphed it. But this one, now look, here's your data. Now the leading coefficient here, 1.89, it's supposed to be 2.07, 2.007. All right, so we're getting up there. And we got a lot of slop in the data, but we're not. And look at the exponent here, 0.395 instead of a perfect 0.5. So we're not doing too bad. Excuse me. We're not doing too bad. And if you do the data, you'll see that the power law, this is the power law trend line. The power law trend line for the raw data measurements, it's got some scatter in it, or slop, as we say. But it's basically following a pretty close to the actual theory. Now, the theory is in black, all right? And the rectangles are where your measurements should have put you for period. The reds are where your measurements did put you for period. All right, that's what you measure for the period. All right, so this guy up here, I don't know about this guy up here. Some of these are, but most of these are, there's a lot of center of mass down here near the theoretical line. So you would want to go back and maybe do another run with this and say to yourself, okay, let's try not to get one of these babies up here. All right, and try to go from a good long run here, from about 1.3 down to about 0.3 and get like 10 readings or 20 readings, and try not to get any slop out here. Just do as careful as you can. Hey, let me ask you a question. It's impossible to see. You know what? I would like to know which group has their data closest to this line. Now, all the groups are mixed in there. They're not identified, so they're all bosonic. So you can't identify them. But if you go back to that data file that I sent, you can look at your group and then program in this graph here, and then see how your group fits. I should probably do that. The problem is it would require 33 groups. It would require 33 graphs, but you could do it. Let me know if your group is right on the black line, or real, like these guys right here. Now this is not going to be one group, but like one group might have something really close here, and something really close down here, and something really close down here, down in this screen. And if that's the case, then you're good. Now, if there's a group that this is 1, 2, 3, 4, 5, then now, but the problem is you can't tell. That might be one group, or it might be a bunch of group. It might be everybody. Every group has a datum that's way out there. All right. So this gives you a clue of where you're supposed to be, and it'd be interesting to do another run on that, see if you guys can get really close to the black line. Now, let me ask you a question. You can all check how close you are to the curve by looking at your data. But let me ask you a question. Who thinks that they have the a real precise period measurement, capital T? What group thinks they have a? Who would say that I have a really good technique? Anybody? You guys? Okay, stand up and describe what you guys did, how you measured T. Listen to you now.
So when we measured our period, we didn't just go one run. We did like 10 runs and then divided by that time. So we get like 10 seconds, divide that by 10, and we get that precise period.
So when you said runs, you mean out and back,
Yeah, then out.
and then out, and you did that 10 times? Anybody do that? Out and back, 10 cycles and then divide by 10? Raise your hand if you guys did that. Okay. Anybody do a bigger number? 20 cycles, divide by 20. All right. The reason that more trials for each length is good is because it means that it diminishes the effect of your reaction time. Okay. Everybody, because everybody in here has a reaction time of about 0.2. Now, that's the basic. I mean, if you look at the reaction time data, that's what it is, about a 0.2. That's the stuff we had up there in web courses. I had reaction times, not this stuff. I'll try to put this data file up for you. Anyways, so you might decide, okay, I'm going to do 20 cycles and then divide by 20, and that'll make your measurement error a little bit smaller. Okay, if you do 100 cycles, even smaller, right? Now, there's a limit. You don't want to do 1,000 because you got to get it done. You don't have all day. But I mean, you could do it that way if you wanted to. All right. Now, so that's my last comment on the pendulum measurement situation. Now, I want to go back to the document. No, I want to talk to you about circular motion, not circulate motion, but circular motion. And let's do some notes from the presentation. So these are just kind of general notes, and then we're going to do a little bit of calculus at the end. If you have, go ahead and draw yourself kind of a curved path, no particular shape. I have two, make them with two different curves though. So my first curve there is a little bit bigger. My second curve is a little bit tighter. All right, so draw yourself a curved path. And one of the things on a curved path in general is that you're changing direction. And what that means is your velocity arrow is changing. So there's an acceleration, right? So the acceleration vector is true even if you don't change the speed. So in other words, you could run through this if you were in a car and you ran through this track at like 20 miles an hour, you would still have a changing velocity arrow even though your speed doesn't change because your velocity arrow is changing. Right? And therefore you have an acceleration vector. All right. Now at each curve, there's what we call a radius of curvature, and it matches the path. The way that we decide the curvature is we say, all right, my path. There's a circle that if I trace it in, at least for a few meters, it's going to be right indistinguishable from the actual path. All right, so what I'm going to do here is I'm going to take a point up here on my path, and then I'm going to try to sketch in the velocity vector and then the radius of curvature circle. Okay, so there's my point, and you guys, the tangent, the velocity on a curved path, I want you to always remember this. Drawing a tangent line, okay? At that point, whatever your curve is, kind of eyeballing a tangent line. In the theory of relativity, in physics 2048, physics 1, and all the way in between, we think of a velocity as something called a tangent vector. And the tangent in the vector, or the velocity vector, is always tangent to the curve, to the trajectory. All right, now that's fantastically powerful when you're working in curved space-time. You got to do this. All right, and it's very helpful for us to think of this as a tangent vector, tangent to the trajectory. Now we could have had, if we were going the opposite direction, the arrow would be the opposite direction, but it would still be on that tangent line. Okay, so we're choosing to head from left to right through this set of curves. So there, let's just say that that's our velocity vector. Okay, so we got the velocity vector, and go ahead and label that V. And we're just going to try to keep it simple here. And now let's vacate the inner space. Now let's try to get the curvature circle. All right, now here I go. There's my curvature circle. Now I'm going to push it. Now watch, look at it now. I'm slightly off the curve. Let me push it into the curve. All right. All right. Now it's an there. I pushed it into the curve. And what we say is that it's an imaginary circle, but we say for just a few meters along that curve at that point, yeah, that's the exact. It's identical to that circle. All right. Now you can see that the circle breaks away from our actual path eventually, but the way that we describe it is at that point there's a curvature. Now if you're a little bit further along, you have a slightly different curvature, and right in here, this is almost a straightaway right here between the two big curves. All right, so that that has a curvature of its own. And then right down here, I'm going to need a really small circle down here. All right, that means you have a tight curvature. All right, so and the main thing is that the center of the way the circles are, the center of the imaginary circle is inside the turn. Now that underline the word inside. The center is inside the turn. I cannot overestimate the importance of that word. Okay? So at this point, the velocity vector is tangent to both the circle and the path. So what we would say, the other thing we would say is this circle is tangent to the path at that point. Now that circle is not tangent to the path hardly any other point. But for that point, yeah. All right. Now, this is kind of a general path, and we're not going to be working with general paths for very long. And let me just point out that a circular path has one radius of curvature, and we're going to work with a big circular path, a very famous one down in Italy in just a few minutes. And it just has one, curvature. But in general, some kind of, like you're on a road out in the countryside and you're going through the curves at 50 miles an hour, or out on the turnpike, or over those guys over at the Daytona, what do you call it? The Speedway. Those guys have 3 turns, okay, depending on how they configure the track. 2 of the same size and then 1 slower turn by the grandstands. I guess that's how it is. Who's ever been up there? I've never been up there. Is that what it is? They have a turn right in front of the grandstands, but it's not a big turn. It's just kind of a graceful, big radius turn. Yeah, that's what I thought. I've only looked at it from Google Maps, so I'm not really sure how. All right, now, if the speedometer is constant, then the acceleration is going to be exactly perpendicular, and so that's the red acceleration arrow. Okay, it's going to be exactly perpendicular to the velocity. Now the velocity is tangent to the path. The curvature circle is tangent to the path. So if something is perpendicular to the velocity, it points straight toward that circle's center. All right. All right, so that's this next sentence. Okay, and the reason for the reason that the acceleration is perpendicular, you think about it, there's no acceleration along the vector to speed it up. There's no, because it's not speeding up. So there's no counter acceleration to slow it down, So it's just perpendicular. So if I say that the speedometer is constant on a curved path, you know that the acceleration is perpendicular to whatever my velocity is. All right, so you go through this set of turns at 20 miles per hour. So you put it on cruise control at 30 miles per hour, for instance, and then you go through the turns, and the accelerations that you feel are going to be left and right, as you make your turn. The first one, you're going to be accelerating to the right, to the inside of the curve. And then the second curve here, you're going to be accelerating to the left, inside the turn. It's always going to be pointing towards the along the radius of that imaginary circle, and therefore it points towards the inside of the turn. And basically what you're saying with that acceleration vector is it's changing the direction of the velocity. So, and it might be a small or large force, but what really changes the value of your acceleration is the speed and then the tightness of the curve or the radius of curvature. Okay. So we're going to, and of course the force, the acceleration's toward the center, and so is the force. I mean, that's what your tires do. Your tires are getting a grip on the surface, and the surface is pushing you towards the center of the curvature at that point, anyways. So the big factors are, and you know this, if you go around, if you're leaving campus out here by the express exit lane over here by University, and you want to turn right to go up Alafaya, to go to McDonald or something like that, or go over to Publix to get some Chinese food, you make a right turn there. All right. Now, if you're a normal, and I know all of you are good citizens and good drivers, so you never speed, but if you're standing there you're a pedestrian waiting to cross, and you hear some tires squeal, that's somebody taking that corner too fast. The tires are squealing because they're losing their grip on the surface of the road, right? You ever hear that? Somebody takes a turn too fast? No, not when they're peeling out, when they're going straight ahead, but when they're turning around the corner and they're going, and you hear that, going around the corner, that's the tires losing a little bit of grip, getting it back, losing it again, getting it back. That oscillation produces a sound, and it's because you're too fast for the turn. Your tires can't accelerate you and keep you on that curve. They're trying to get you to a bigger curve where they don't have to accelerate as much. So the tightness of the curve and the speed, they have opposite effects. Okay, so big speed requires good tires. Big curve, big radius of curvature requires granny tires. Or you could, hopefully nobody in here's got bald tires or running on there. Did you ever see somebody that's so broke that they're running their car on the little fake spare tire? Hopefully you never see that, because it's really dangerous to do that for more than. But I had a friend when I was in grad school. I had this friend. He was a good guy, but he was kind of a derelict. And for months he was running his little Ford Fiesta or whatever it was on the fake spare tire on the front. I almost broke down and bought him a tire, but a new wheel. But I don't know. He eventually got it fixed. Anyway, so the speed and the tightness of the curve are the thing. Now, let's take a look at a real example. Now, this is called the Nardo Ring, after a city of Nardo in southern Italy. And what they do is they have in the Boot-Heel of Italy, the city of Nardo, they have a test track. You can see it here from space. It's a little bit closer. And this is from Google Maps, I guess. This is from Google Earth. It's a little closer. And that's a test track. It's a Fiat test track. Test track. Um, and everybody in Europe uses it. I don't know, maybe Americans use it too. And you can see it's pretty large, right? And if you're driving on the Nardo ring, you use the bank. It's banked. It's a banked ring, and they actually have two rings that they use. The outermost lane is configured for 149 meters optimal, 145 miles per hour optimal speed. So when you're on, it's banked. So when you're at that speed, your steering wheel is straight, and they just run that thing around. You know, if you're on a Google, no, what do they call those things? A Tesla, you could just set it and you bail out and let your Tesla take laps around that, and you don't have to steer at that speed. And so they do endurance testing and stuff. See if they can make their cars fall apart, find out where it falls apart, and then fix it before they produce it in mass quantities. Now, if you go faster than 149 miles an hour, you got to crank the steering wheel a few degrees. Okay, and you don't want to go less than 149. But all right, now they have another lane for testing trucks, and that one I think is about 50 miles optimal speed. So, over there in Europe, they have the autobahns up in Germany. I don't know. Has anybody ever done much driving around in Europe? Anybody here? Do they have like high speed, like autobahn type highways anywhere else than Germany? You don't like it? Yeah, yeah. So, the interstate highways here in the United States were designed, President Eisenhower, he was the supreme Allied commander in World War II, and he loved the German autobahns. He said, we got to have something like this in the States. And so that's why we have an internet. The interstate system, it was originally conceived as the def, defense for defense, national defense. Eisenhower said, we want this highway system through the United States, and it's going to be for national defense in time of war. And that's what he was thinking. And so, did you know that the rules are for designing an interstate, they have to have a 1 mile straightaway, like at least once every 20 miles or something like that. Did you know that? And that's so they could land planes on it. And then, you ever notice that they have the side roads? And they have the big median, and then they have the huge from the most places, except like in cities like downtown Orlando, they between the edge of the road and then the regular buildings and stuff. There's a huge gap. They make a big, huge side area that's clear usually. Okay, so there's a clear area beside the road. There's a frontage road. Then there's the clear area. Then there's the interstate, one direction. Then there's the middle median. It's big usually, as big as they want. Then there's the other direction, the other lane of the interstate, and then there's another big open area. And the reason they do that is so they could, they design it so that we can move tanks and trucks and stuff without, over in Europe, they had very difficult time moving their armor and their trucks and stuff because the road network over there, except in Germany, was really bodacious, very small and not organized. And so that's why we have the National Defense Interstate Highway System. But out in Montana, speaking of the Autobahn without any speed limits, out in Montana, the entire state for many years was no speed limit. When I was living out there, and because it's just they say at night there was a speed limit, but during the day you could drive whatever you thought you could do, and the cops wouldn't nab you for speeding. But they could nab you at night because they said, drive at a certain speed limit at night, but during the day. But then the feds, some politician in Washington said, oh no, if you're taking federal funds, you have to have a speed limit. And so, and Montana has all these huge interstate highways. They go, long distances. It's a big state. And that's why people drive so fast. So you know what they did? So instead, okay, we'll have a speed limit. We'll put the speed limit at 70, which is what you want. And so, but then, you know what they did? They made the speeding ticket $5. So that and no points. So I wish it was like that here. Speeding tickets here are like $160 or more. It's unbelievable. There's cops in the state. All right, so anyways, on the inner lane, you go faster than the optimal 50 miles an hour. You got to crank the steering wheel a few degrees, etc. Now, here's a kind of a perspective view of a car. Actually, that looks like a robot-driven car. What is that? That's like an El Camino from the 70s or something. Anyways, so this guy's turning left, and he's got his wheels cranked to the left. So now what we're going to do here, we're going to derive a couple equations on a circular path. And so we're not going to do the general path. We're going to have a good constant speed circle. So uniform circular motion means constant speed, circular path. Okay, so no variation in the radius of curvature. So here we go. Okay, draw yourself a circle and go out to the 3 o'clock position and put a dot, and let's just call that the position of the vehicle at time t1. All right, draw the radius in, and we know it's uniform speed, constant speed, so the velocity vector is tangent to the circle, and it won't be changing in size. All right, so it's a circle. Velocity is always tangent, and because it's not changing in size, if we go a little bit later in time, say at time t2, I know I'm going to have a velocity vector like that. So try to make that secondary. So that's like at 2 o'clock, all right? And so we're going counterclockwise around this circle. So this is us going around the Nardo ring at in a counterclockwise manner. Okay, Tristan? So what we're going to do, we're going to take, so this is 2 snapshots in time. So we have 2 radii, and we have 2 velocity vectors. And let's just kind of, all right. Now, I want you to take and copy the radii, the radius from T2, and copy it over to the first circle. All right. All right. So those two, and just kind of copy them down. Now, I also want you to copy the velocity arrows. So here's the velocity arrows. Okay, so kind of copy and park that up to the other side there. All right. So they form kind of a V shape. Okay, so the black ones are the radii, and the red ones are the velocity arrows. All right. Now let me park my 2 circles up here to the side and make my 2 V's a little bit bigger. All right. So up on the upper left, that's kind of the legend. Those are our 2 snapshots. And we've kind of distilled out the radii, and we've connected them. So the 2 radii meet at the circle's center. The 2 red velocity arrows meet at the location of the object. Okay. All right. So the velocity triangle is a little bit abstract. All right. The other ones you just copy them right over because they both touch at the center. All right. Now go ahead and connect the dots for the position triangle. Now go ahead and label the distances R and R. All right, because that's what they are. We're on a circle. Okay, so we're not doing that kind of generalized curve. We got a perfect curve, a nice uniform circle. So the distances are R and R. And the approximate change of position or distance is this straight line. Now the actual motion, the actual mileage would be along a curve, a circle, an arc of the circle instead of that straight line. So that's why I say it's approximate, right? Now let's do the same thing up here for the velocity triangle. Let's make a velocity triangle. And we'll label the sides there V and V. It's uniform circular motion, so the speed is not changing, all right? And my acceleration is going to be perpendicular to whatever my velocity is. Now my velocity is changing, but at any point in time, if the speed is not changing, I'm going to have an acceleration toward the center of the circle. So we're going to see that in a minute. Okay. So now, what's the name of this dotted red segment between the two velocity arrows? What would you call that? No, that's not it's related to acceleration. Delta V, delta velocity. All right, so go ahead and mark that one as delta V. All right, now what can you say geometrically about these two triangles? They have the same angles, right? And therefore, they're proportional, right? So we have two similar triangles. And so the angles are equal, the sides are proportional. And I'm emphasizing the word proportional there because you can't mix apples and oranges. You know, you can't say, well, I'll just multiply the radius by 2 and that'll be equal to the velocity. It may look like that, but you don't multiply, you don't magnify or shrink down a distance and get a velocity. But you can at least say that they're proportional. All right. You know, whatever the proportions work out to be. All right. What's a fancy name for these kind of triangles? Yeah, isosceles. That's right. Right. So these are isosceles. And what's true about what's true about the two base angles of an isosceles triangle? They're equal. Or what we would say in 10th grade geometry, they're congruent. Okay. They have the same size. So that means that all the angles here are the same size. All right. Now, this is the key. That distance, that straight line, is approximately V delta T. So T2 minus T1, that's the elapsed time. All right. And that elapsed time times whatever the V is going to be approximately that distance. Now, V times delta T is going to be exactly the length of the arc, right? But we're trying to work with triangles here. Okay, so the position triangle is approximate, right? Now, the velocity triangle is exact. That's a good delta V over there, all right? So let's write down some proportions. Okay, we've got the base is of the position triangle is V delta T. The base of the velocity triangle is delta V. And then the long sides are R and R, and then V and V for the velocity triangle. All right. So here we go. Long side over long side is R over V. Okay. And that's going to be proportional to base over base. Now, the numerator of both sides of this proportion come from the position triangle. The denominators of both sides of this proportion come from the velocity triangle. Now, I couldn't make that type into red type, but but the V and the delta V are obviously from the red velocity triangle. Okay. And this is going to be, so it's proportional triangles. And this is actually going to get us an expression for the acceleration. So make a note, isosceles sides. So this is position dot speed. Position triangle dot speed triangle. Position on top, position triangle data on top, speed triangle data on the bottom. All right. And then this one, this is from the, let me get this over here. The isosceles for that's base over base for position and speed on that side. All right. Now let me ask you a question. I want you to look at that equation really carefully, that proportion. All right. Look at it carefully. Do you see an acceleration in there? Raise your hand if you see an acceleration. Who sees an acceleration? Okay, back there. Anybody else? Anybody else over here? Okay, how about Sean? Okay, let's go to the back table boys, the back table gang. Sean, what do you got? What do you see? Where's your acceleration? I don't see an acceleration there. I don't see any delta V over delta T. Okay. So yeah, good. Is that what you were looking at, Diego? Is that what you were looking at? It's inverted. There's a delta V over delta T, except it's upside down. All right, let's get it right side up. Ding. So the acceleration at least for these triangles, is v squared over r. Right? Now, my wonderful students, let me go to the doc. You put me on the doc cam for just a second. I'm going to write something down here. I'll draw this down at the bottom of the page. df by dt, the definition is the limit, your ever-loving limits. When I was in undergraduate, I hated limits a lot. But f of t plus delta t minus f of t divided by, what goes in the denominator here? Delta t. And this is the limit as delta t goes to zip zap. All right, so that's the definition of an acceleration. All right. Now just think of, this is v. So another way that you could write it, the limit, so this would be dv by dt, would be the limit of v of t2 minus v of t1 divided by delta t, defined as delta t being equal to t2 minus t1 in the limit delta t going to 0. Now, what would happen to the triangles as delta t goes to 0? Let's go back. Can you put me back to the laptop, please? What would happen to those two triangles? Okay, so you see the derivative over there, delta v over delta t. That's the derivative. We're going to make that into the derivative. But what would happen to these triangles if we made delta t smaller and smaller and smaller? Well, more precision, Noah. No, not closer to delta. No. So what happens to the V is constant. So what happens to the position triangles? Delta T gets smaller. Come on, think. What happens to the triangle? What happens to the sharp angle of the triangle? That angle goes, it gets sharper and sharper. Delta, the top angle, the sharp angle gets smaller, smaller, smaller. So now, what is your name again? Over here, Kathan. Kathan, you were saying that, you were thinking that, but you didn't say it exactly right. So what would happen is the triangles would get more and more slivery, right? And that corresponds to delta t going to 0. And that so really what we have here is the acceleration, the second derivative of the position with time, with respect to time, is equal to v squared over r. And let's think about this. Okay, so the acceleration, all right, if v gets too big, you're going to need a lot of acceleration from your tires on the surface of the street as you turn from University into Alafaya. And if your tires don't have enough grip, they're going to squeal, right? So V on top, and in fact, it's V squared on top. So little changes in V are going to have a big change in the overall quotient. Now, the granny effect. If R gets bigger and bigger and bigger, that means your acceleration is smaller and smaller and smaller. So if you want it, if you don't want to get rattled back and forth, you don't want to hear squealing tires, just make a nice big wide turn. All right. And this is the formula for what we call centripetal acceleration. All right. And it's basically because we have proportional triangles. So the speed triangle and the position triangle, and then doing a little bit of infinitesimal calculus with the limit as delta t goes to 0, it gives us this basic formula. And the word centripetal, I want to give you an admonition. And my admonition is this. Do not say centrifugal. Centrifugal. Now you can say that over in the student union if you're eating your lunch and stuff. But if you're in this room, don't ever say it. Okay? It's a centripetal. Now, what does that mean? Centrifugal, fugue, F-U-G. That means to flee, fugitive. Fugitive means to flee. If you're a fugitive from the law, you're trying to escape the law. You're fleeing from the law. Okay, so that's the Latin word fugere. Okay, so centrifugal means away from the center. You're fleeing the center, center. Petal means toward the center. Okay, so centripetal means toward the center. Do not get those words confused. All right, now sometimes I even catch myself napping, but do not let me catch you napping, especially on quiz number 1. Ooh, how could I do a trajectory problem that has centrifugal accelerations in it? Cool. You go around a corner and off a cliff. Sweet. Even better, you launch something out of a catapult or one of those trebuchets. Those things are pretty awesome, actually. Of course, they don't compete with a 16-inch gun on a battleship. And when we start talking about centripetal forces, or when we start talking about Newton's laws of motion on Thursday, um, we'll talk about the forces involved here. But a sneak preview, whatever the acceleration's doing, it tells you what the forces are doing, and vice versa. Centripetal acceleration. Let me ask you a question, if I may. The force of gravity. Okay, now Earth's going around the sun in base pretty close to a perfect circle. It's a little bit elliptical, but pretty close. Force of gravity. Acceleration on the entire planet of Earth due to the gravitation of the sun. Centrifugal or centripetal? Centripetal, it's towards the center. Gravitation is, and you can read about that in chapter 5. Now, I want you to finish studying chapter 4, and just to get you guys motors motivated for quiz 1, I want you to try to work as many examples in chapter 4 as you can. And that is a gigantic tip to prepare for exam for quiz 1. Okay, you're dismissed. I'll see you guys. We're dismissing a little early today. I'll see you Thursday.